Hello, my name is Yoder, and this is my research on the development of the Bombardier Beetle fire extinguisher, a CFD model investigation. The main goal of this research is to create a novel fire extinguisher that utilizes the defensive spray mechanism of the Bombardier Beetle and incorporates that into a fire extinguisher operated by one man as seen in the photo. First start by talking about the characteristics of the Bombardier Beetle. When threatened, this beetle can facilitate a chemical reaction in its abdomen involving hydroquinones, hydrogen peroxide, and oxidative enzymes that creates a hot vapor in its chamber and creates high pressure, which when it's released creates high velocity of about 11.63 meters per second, which pulsates at frequencies of 531 hertz. And the combination of the high velocity and the pulsations create a throw distance of about 200 times the chamber length of the beetle. There are many ways in which the spray mechanism can be implemented into modern engineering technology, such as drug delivery sprays, fuel injectors, aerosol sprays, and as I'm trying to do in this research, fire extinguishers. This spray would improve current fire extinguishers primarily in three ways. First, by increasing the range of the fire extinguisher. Second, by increasing the accuracy. And thirdly, by supplying an added blowing force from the pulsation. There were a few design decisions that we made that differ from the actual Beetle. Primarily, we decided to use water instead of chemicals because it is more cost-effective, safer, and more readily available. So to achieve the same effect of the Bombardier Beetle, we need to vaporize the fluid within the chamber to create that high pressure that will drive the velocity. So the first thing we did was select the heater with which the chamber would be built around. So we decided to select a cylindrical cartridge heater similar to the one you see on the right. We then designed a heater sheath around this, and leaving a little bit of gap for water annulus, and then finally a metal outer casing. So pictured here is an engineering drawing of the chamber used in this study with the cap removed. As I had mentioned previously, that center cavity is where the cylindrical heater would go, which is surrounded by a heater sheath and a little gap left for the water annulus, which is encased by a metal outer casing. All the dimensions used for this chamber can be seen in the figure. Below is the spatial discretization or mesh of the chamber with the cap on. It consists of about 119,000 cells, and as you can see from the figure, it is split into a variety of sections to allow for a more structured mesh. There are a few important locations I'd like to point out here. That center cavity is again where the heater would go, and that is the surface with which the heat flux is applied for the CFD model. Directly above that, there's a little circle, which is the liquid inlet, which is supplied at 1 meter per second. And in the top right, you can see the difference between the yellow front section and the gray back section. That is the interface between the cap and the body. This research, we decided to make a three-step plan. Firstly, we wanted to create a simple model with multi-phase flow from vaporization as a baseline. Secondly, we wanted to perform verification studies on various CFD degrees of freedom. This table shows all the different models run so far. Model number 1 is of course the baseline mentioned previously. We then decided to look at time step size, multi-phase models, and mesh refinement and their influence on the results. And lastly, we wanted to implement cyclic flow, as this is an important feature of the actual Beetle spray mechanism. So next, I want to talk about the various mesh resolutions used in this study. This first figure is a side view of the starting mesh, and as you can see, it is very structured, but also very coarse. Next is the first refinement, which takes each volumetric element of the starting mesh and cuts it in half in each of the 3 Cartesian coordinates, resulting in an 8 times increase in the total mesh. This was then done for the second and third refinements as well. Next, I'd like to go over the CFD settings used in this study. We used the standard K-epsilon turbulence model, the inhomogeneous Eulerian multiphase model, with no heat transfer coefficient between phases, an algebraic calculation of the interfacial area between phases, and the Lie evaporation condensation mass transfer model. These are the under-relaxation factors used for this study. I'm not going to go over them in depth, but these are the default values used for the CFD package that we use. We use the simple pressure velocity coupling, the least square cell-based gradient spatial discretization, and first order upwind discretization for all calculations. So here are the results from the baseline case. These are various variables we tracked as the simulation progressed, and these are the final steady state variables. We looked at maximum fluid temperature, maximum heat surface temperature, normalized outlet vapor mass flow, maximum volume fraction of vapor, and total volume fraction of vapor. What we learned from this is that there is significant vaporization just even in this very simple baseline case. The temperature is well above vaporization temperature, and there is almost 35% vapor in the chamber. There will be a few contour plots coming up in later slides, and I just wanted to give a brief description of what those contour plots are. You can see in this figure is our chamber geometry. So you can see again that middle cavity is where the heater would go, and directly above that is a little blue circle, which is the liquid inlet. If we take that same figure and take a vertical cross-section of that, we see a cross-section of the chamber itself, and also a cross-section of the water annulus, which forms this sort of C structure. If we rotate that to be face on, we see that C structure very clearly, and that is the contour plots that will be shown in future slides. So here we see a contour plot of that C structure I was describing previously of the fluid, and this shows volume fraction of vapor, where low volume fractions are blue and high volume fractions are red. What we see from this is at the inlet there's completely water, but at the outlet we're getting at least 50% vapor. This next contour plot shows fluid velocity, and again at the inlet it's coming in at slower speeds, but at the outlet it increases by at least 50%, and this shows the viability of this vaporization scheme for a fire extinguisher. So this table shows the results from the verification studies. Each of the percents listed in each of the categories is the percent difference from the previous model. So for example, the first time-step model is contrasted to the baseline model, and the second time-step model is contrasted to the first time-step model. So looking at the results in yellow, which is the results of the time-step study, we see that each of these do not vary much from the various cases they're compared to, which indicates that the model is time-step independent. Looking at the results in blue, however, we see significant departures from each of the models with the various multi-phase settings used. It indicates that these should be investigated further for use in future models. And lastly, looking at the results in green from the refinement studies, we see that again, similar to the multi-phase settings, there are a few variables that are significantly different from each refinement, which indicates that we need a model that is even more refined than the third. So below shows an animation of that same fluid cross-section I described previously with the implementation of cyclic flow on the baseline case. This animation shows fluid velocity, where high velocity is colored in red and low velocity is colored in blue. As you can see, there is this kind of wave-like high velocity, low velocity connection between the inlet and outlet. This cyclic flow was created by having a sinusoidal velocity at the inlet and a sinusoidal back pressure on the outlet, which is offset from the inlet to create times of low flow in and low flow out to allow the vapor to vaporize in the chamber, and then allowing the outlet to be throttled out at high velocities. What we learned from these initial studies is that they show promising results that this spray mechanism is viable in a fire extinguisher. However, more verification studies need to be run before we can be confident in our results for use in an actual prototype fire extinguisher, primarily in multi-phase settings, turbulence settings, and mesh resolution. Here are the references used in this study. If you have any questions, I'd love to answer them, so feel free to reach out at the email posted here. Thank you.